Hello. In this video, we describe how lunar gravity affects Earth satellite orbits and how to include it in the satellite equation of motion. The image on my left was copied from Wikipedia. It shows tidal forces on Earth's oceans due to lunar gravity. In this image, the circle represents the surface of Earth. The blue arrows are acceleration vectors due to lunar gravity relative to the Moon's center, and the red arrows are acceleration vectors due to lunar gravity relative to Earth's center. It is the latter that produces the forces that alter ocean water levels. To get the acceleration vectors due to lunar gravity represented by red arrows, we must subtract the acceleration vector due to lunar gravity at the center of Earth from the acceleration vectors due to lunar gravity at the surface locations. Why? It's because Earth is also being accelerated toward the Moon, and it's your reference point for measuring these accelerations. Remember that the center of Earth is the origin of the Earth-centered inertial coordinate system, and all acceleration vectors must be measured relative to that origin. Here's a simpler explanation. Suppose that you're on the surface of Earth with the Moon directly overhead. You are closer to the Moon than the center of Earth. Therefore, you experience a larger pull from the Moon than Earth does. Effectively, you weigh less when the Moon is overhead. Since ocean water also weighs less here, the result is high tide. Now suppose that you're on the surface of Earth opposite the Moon. The center of Earth is now closer to the Moon than you are, and therefore experiences a larger acceleration from lunar gravity than you do. Relative to Earth, then, you feel an opposite acceleration from lunar gravity. Again, you weigh less than you would without the Moon's gravity. This explains why there are 2 high ocean tides per day. The same thing occurs for satellites orbiting Earth. Note that I've changed the previous image to demonstrate this. In this new image, Earth is shown at the center, and the outer ring represents the satellite's orbit. Note that the acceleration vectors on the backside of Earth are pointing away from the Moon, while the acceleration vectors on the front side of Earth are pointing toward the Moon. In both cases, the relative acceleration vectors are pointing away from the center of Earth. This is how accelerations due to lunar gravity tend to distort the orbits of satellites around Earth. Depending on the orientation of the orbit relative to the Moon, it can stretch a circular orbit into an elliptical orbit. In summary, when solving a satellite's equation of motion based on Newton's laws, to include the acceleration due to lunar gravity, for each satellite position, you must find the gravitational acceleration vector due to the Moon at the center of Earth, and then subtract it from the gravitational acceleration vector due to the Moon at the satellite. If the satellite is close to Earth, the 2 subtracted vectors are nearly the same in magnitude, resulting in a small acceleration magnitude that produces little effect on the satellite. If the satellite is close to the Moon, the lunar gravity vector at the satellite is much larger than the lunar gravity vector at the center of Earth. Therefore, lunar gravity dominates, and Earth's gravity has little effect on the satellite. In other words, the method that we just described for including lunar gravity in the satellite equation of motion is valid for all near-Earth orbits, including lunar orbits. There is no need to do a coordinate transformation or change the equation of motion when traveling from Earth to the Moon. If you find this video useful, please give it a like. If you want to be notified when we add more videos, click on the notification bell. Finally, if you have comments or requests for new videos, please leave a note. Goodbye.